Hi, welcome to AWS reInvent. Today we're talking about 12-factor serverless applications. A little bit about myself. My name is Mohib Zara. I'm with the Serverless team. I'm a senior developer advocate. A little bit more, I've got a background in IoT, robotics, and art installations, and working with nonprofit hackerspaces. What we're here today to talk about is the 12-factor model as it pertains to serverless applications. The principles of a 12-factor application was popularized by developers building large-scale applications on platforms such as Heroku. And in recent years, these 12-factor guidelines have been considered best practices for both developers and operations engineers, regardless of the application use case and at any scale. Many of these 12-factor guidelines align directly with best practices for serverless applications and are improved upon by given the nature of AWS Lambda, Amazon API Gateway, and other AWS serverless services. However, these guidelines don't directly align with serverless applications. They're somewhat differently interpreted, and not all of them apply, but can be used to really improve how you go about building and developing your application using serverless. Now let's talk about what these 12 factors are. So the 12-factor app is a methodology for building software as a service apps that use declarative formats for setup automation. This is to minimize the time and cost for new developers joining the project. So you don't want somebody coming in and spinning up half their ramp-up time just trying to figure out where everything is and how you go about actually deploying and building an app. You want them to be able to just get in there and start building. You want to have a clean contract with the underlying operating system. This offers maximum portability between execution environments. Short, you want to build your code such that no matter what machine your developers are building on, where they're building it, they're not going to run into these dependencies that are very operating system specific. Then you want apps that are suitable for deployment on modern cloud platforms. This obviates the need for servers and system administration. Right? Then you want to minimize divergence between development and production, this enabling continuous deployment, and this gives you maximum agility. Right? You want to make sure your various branches of deployment are as similar as possible. Then you want to be able to scale up without significant changes to any of your tooling, architecture, or development practices. Right? So this is being able to scale, just you have your code and it can scale and you're not changing anything else around that. You don't want to have to go back and change a huge code base because suddenly you're getting much more traffic than expected. That should just be able to be done without any effect to your code. Let's get into what is a serverless application. We won't get too into what that is, but at its base, the idea of a serverless application is to create a decoupled application. So where your storage, your compute, and your event sources or entry points are all separated. With AWS, this can be done very neatly, where looking at the slide, you start with your event source. Now this could be a change in data state on a database or some other event along the system. It could be a request to an endpoint through Amazon API Gateway or changes in some other resource such as a policy change. And then that invokes a Lambda function. Now this is your compute layer. This is where with AWS Lambda, you can run multiple different runtimes, and we have a number that are initially supported, such as Node.js, Python, Java, C#. And we also have a runtime API, which allows you to bring in your own runtime. We've seen developers choose all sorts of interesting custom runtimes, such as COBOL. And then from your compute, you can now trigger all your different resources now. Is that entering into a database, a new data set, or interacting with other services, third-party or native. So that's what builds a serverless application. And some of these common cases for using AWS Lambda in serverless applications, we've seen web applications, static, complex. We've seen backends for mobile, IoT, various other apps and services. Data processing is a common case, taking an image, say upload it to S3 and then running that through a Lambda function so that it can be resized, processed, run through machine learning algorithms. It's been used quite a bit in chatbots. It's what powers a lot of the Amazon Alexa applications and Alexa skills. And of course, in IT automation, you can have whole workflows triggered from a policy change event and run all sorts of remedy situations on those, as well as managing infrastructure existing and new. So let's explore what these 12 factors are. We'll go into each of these one by one, and we'll also mention where they apply to serverless and where they might not necessarily apply to serverless. Starting with the first factor within the 12 factors, we start with Codebase. That's one Codebase tracked in revision control with many deploys. All your code should be stored in revision control now. That could be code commit if you're using AWS services or GitHub or Subversion. And that's just a general best practice. You should always have your code in some versioned repository. Now, these should be then broken up based on shared events. In the case of, say, a Lambda function project, you'd be using, say, for example, an Amazon API gateway as your event source, and now that's your REST endpoint. And those should be shared common between your functions within that repository. If it's a different event source or different set of events or different API, then you should break those up as necessary. This reduces confusion and keeps your code quite clean. And then second, we have dependencies. Explicitly declare and isolate dependencies. Code that needs to be used by multiple functions should be packaged into their own libraries. Now, these can be files or data sets, so they can be different libraries and dependencies. But as your code base builds, you want to make sure if there's common libraries, instead of repeatedly applying those where a lot of errors can occur, where a developer might not know what they need as you continue to grow, it's best to keep those in what we call layers. So we have a bunch of different ways to do that. So if you were using a Node.js runtime for your Lambda function, you could create a layer with just a zip file, where at the root directory you've got all your Node modules. And going forward, same with like Java and C#, there's different conventions to follow. And so that's how you create a Lambda layer. Lambda layers are kind of these files that they're shared dependency files. And once you create a layer, you can share it by version as needed throughout your organization and within your application. And layers can be anything. Again, as I mentioned, they can be training data or configuration files. And this promotes a separation of responsibilities. It lets developers iterate faster on writing the business logic, focusing on what they want to build instead of what they're missing or what they need. And this has built-in support for securing sharing throughout the ecosystem. And using a Lambda layer, right, we talked about you can create a zip file with all your dependencies. And these are immutable. So once a Lambda layer is created, you can version it and manage updates this way. If you're changing things across your org, your various different applications should still be fine. And when a version is deleted or permissions to use it are revoked, functions that used it previously will continue to work, but you just won't be able to recreate those Lambda functions without having to apply a new layer. Now, this allows, so if you were to remove a layer, you don't have to worry that your existing applications throughout your org won't suddenly be deprecated and unusable. And you can reference up to 5 layers. So, and one of those can be a custom runtime, as we mentioned earlier. So we have that runtime API. You can create that, put it in a layer, and then apply that to your Lambda function. And now you have access to that runtime, as well as various resources. So going into number 3, store config in the environment. So with serverless applications, there are many ways to do this. One is you can use Lambda environment variables. When you create a Lambda function, you can define these through the SAMCLİ, which we'll talk about later, or we you can define them directly there in the Lambda console. And now your application, for example, if it is Node.js, you can just call process.env just as you would if you were writing code locally, and it'll have access to all those environment variables. You can also set through API gateway stages. These are key value pairs available for configuring API gateway functionality. And you can pass these on through HTTP endpoints as URI parameters or configuration parameters, and then these will go on to the Lambda invocation. Then there's also AWS Systems Manager parameter store. Now, this allows you to, based on roles and permissions, create a number of just sets of your different parameters and environment variables. This way, when you're kind of stubbing out through your different stages of deployment, you can do this all in one place and then just have a secure encrypted way of accessing those variables through your application. In this slide, we have an example of using Boto3, which is the AWS SDK for Python. Call in this systems manager utility function, which allows you to then request those. So we see in this defined function get parameters, we just ask the SSM library to call for the Lambda secure string, and then it'll pull it in, and then now your code has it. So instead of worrying about configuring at every step or having your stuff secured, you can always have it through AWS. And this prevents things like when you deploy code in your repository and you've stored your secret values and variables within your code. This prevents that from ever happening. Because once that happens, there's no going back. You'll have to redo all of your security keys. So it's a good best practice to follow is to use all these different methods for securing your variables environments. Number 4, backing services. Treating backing services as attached resources. Now, when we say backing services, we mean things like your database and your other data sources, all these resources that your application will use. Now, this is one of the factors that has no differences here in serverless apps, because by its very nature, resources through AWS and a Lambda function are already attached. So you don't have to worry about setting this part up. This is just done as a result of using AWS services. Number 5 of the 12 factors, build, release, and run. So strictly separate build and run stages. This is, again, one of the factors where there's not many differences from whether you're building a traditional web application to a serverless application. You just got to follow the best practices for continuous integration and continuous delivery. Through AWS, you can use code build and code pipeline to support this. So for example, here with AWS code build, you can just have this file, a build spec, where you define, what are your environment variables, what are your phases of build and deployment, and then you can do these post builds where you define, okay, now, once you've installed my dependencies and all my dependencies for the build environment, go and run my tests, then deploy to CloudFormation, and then also create these artifacts. Part of this factor within the 12 factors is to keep in mind your build, release, and run stages should never have code changes done in between. It should be very much a linear process. You don't want to build something, then release it, and then somebody edited something in a release artifact before it went to run, because now that code isn't tracked, right? So keeping it from your build process, from when you push it to your versioning with this code commit, git, having that run your build spec with code build, and then testing it and running through, creating your artifacts, uploading them, and then running your release. All those changes should be tracked beforehand. So, of course, again, describing more of this file, right? We have installer packages and our run commands, our syntax for creating our artifacts, and then pushing that to be run. So this is an example of a minimal developer's pipeline, right? So we have our 3 stages. We have, at the beginning, we have our source. We push to code commit that builds, and then it runs our dev deploy. And we can run our stubs here for our different tests, our different deployment stages. And so, and this is, you can use SAM or CloudFormation to handle all these building, and we'll talk about that in a sec. Another example, this is much more, many more layers to this. This is where if you were in a production pipeline, you would have, again, your code. You would push it to code commit. It would build in code build. It would go through deploy testing and then deploy staging. And then you could have things where you have a QA step where you trigger off a notification, a text message, or an email, and wait for approval before going to prod. This is really good practice to do this because then, again, you're keeping your code base separated well. You're keeping the differences between your different stages and environments very minimal, and then adding in steps to ensure that before you get to prod, all code is good and set. But again, there's no differences between those steps along the way, those stages and those environments, aside from your variables. All right, so number 6, execute the app as one or more stateless process. So in this case, this is just an inherent property of how Lambda is designed. Lambda functions are stateless. They should be treated as such. You really shouldn't store anything in memory in a Lambda. It lives and dies. It's invoked, starts up, it has whatever memory it has while it's live, and then after that, it might die, or you might have, if you have concurrency, you're going to have multiple Lambdas. So there is no promise of being able to reuse an environment of any single Lambda that's been invoked, because you'll run into things like race conditions where you're trying to hope that your state is still stored in this Lambda, but by the time you come back around, it's all gone. So that kind of data should be stored outside of Lambda and served through like a database or through a cache. So number 7, port binding. Export services via port binding. Now this is something that does not apply to Lambda or to serverless applications. Instead of ports, Lambdas are invoked via triggering services or AWS APIs for Lambda. So you're not having to set up server routing. And this is one of the big parts of why people choose serverless. You're not dealing with the nitty-gritty of host name mapping and server routing. All that DevOps is put away. You just focus on creating your compute and adding your event sources. And Lambda functions can be triggered in 3 different models, right? They can be triggered synchronously, asynchronously, or pull-based. And instead of having one function support multiple invocation sources, create independent functions. So if you have one that receives from API gateway, it should only exist for that. If you have another source that might be a resource change, that should be a separate function. And then you separate that nicely within your code. So let's talk about this Lambda API. This is the API provided by the Lambda service, and it's used by all the other services within AWS. So now when you have these different event sources, they're using the same API, which you can also use through the AWS SDK. It supports synchronous and asynchronous messaging, and it can pass any event payload structure that you like. So this could be an image blob, it could be a JSON file, whatever. It's your event. It's whatever data you want to send into your Lambda, and then you do all of that within your function. And this client is also included in every SDK. So whether that's the JavaScript, AWS SDK, or Boto 3 for Python, etc. Here's the Lambda execution model. So like we said, synchronous, asynchronous, and pull-based. In a synchronous example, you have an Amazon API gateway endpoint. So in this case, /order. You call it and go straight into your Lambda function. Then you can reply back using RESTful methods. And then you have an asynchronous event. This could be something happens in Amazon SNS where a notification is kicked off from some other workflow. Then you can have your Lambda function respond, or an S3 upload. Then you have pull-based, right? These are any changes to data sources or resources. So something gets added into Amazon DynamoDB, somebody inserted on a database, or data was pushed into an Amazon Kinesis data source. It all goes right to, you can send it all into the Lambda service and to your Lambda function. Next, we'll talk about concurrency. This is scale out via the process model. Having to actually handle this does not apply with serverless and Lambda functions, they're designed to scale automatically based on load. You can fork these threads inside of your function execution, but there are practical limits due to memory and CPU network constraints. And so it all depends on how you configure your function. But one of the lovely things about this is that you're not, over provisioning to handle load. This is all managed within AWS. Let's talk more about how you can tweak your function's compute power. So Lambda only exposes a memory control, but that memory control scales the CPU and network capacity proportionally. So if your code is CPU, network, or memory bound, it might just be cheaper to choose adding more memory to your Lambda function. So we did this test where we have this Lambda function that calculates 1,000 times all prime numbers less than or equal to 1,000,000. So there's a high computational task. And so if you look at when the Lambda was set to be limited at 128 megabytes, it took 11 seconds and cost, a little over 2 cents. Now, as we scale that, the memory, we see that the time it takes is less, and the cost doesn't really shift that much. When you look at 128 megabytes versus 1,024 megabytes, so that's 100 versus a gig, we see that the cost relative to that is not that bad, but you're saving 10 seconds of compute. So in a large system, this could mean quite a bit. This could mean, success or failure, and it's negligible costs. Next, disposability. For an application, you want to maximize robustness with a fast startup and graceful shutdown. So this factor only half applies within a serverless application, since shutdown doesn't really apply. That's not something you need to be concerned with a Lambda function. But invocation, whenever a Lambda is invoked, if it hasn't been on for a while, that's when it takes some time to start up. So that startup time does matter. And there's a number of factors to that. What's the package size, the language used, what runtime you're using, if you're using a VPC or not, or any other code that needs to be handled on boot of your function. So we talked about layers. So if you're using really large layers, reaching to the 250 megabyte limit for those, then you might find that might slow down your function. To get more visibility within this, we have a tool called AWS X-Ray. Now, this gives you kind of this overarching view of all your resources within your system. So you can see what's taking the most time, what kind of requests are holding things back. It captures all of that. This is like when you use the inspector in a browser to see all the network traffic, it's like that, but a little bit more comprehensive. An API gateway inserts a tracing header into all HTTP calls, as well as reports data back to X-Ray itself. And so you can see in this example here, this little snippet of code, you can just wrap your SDK calls within X-Ray. Here's an example of what some of that inspection might look like. So you can see down to the milliseconds what's taking up all your time. You can use this really improve the speed of your function. So you watch what's slowing you down. Maybe you're making an API call that might not be the right call. Maybe it's calling too many other services or taking too long. And you can find maybe a more efficient call to make. There's a lot of different things that you can do by just, getting that visibility within your application. So number 10, dev prod parity. So keeping development, staging, and production as similar as possible. Now this is made really easy with serverless applications. You can make use of those environment and staging variables or the parameter store for configuring all your information between your different stages. You can use the serverless application model to deploy your application, and within there you can pass in your different environment variables and stages, all the different mapping. And then having a good CI/CD process, continuous integration, continuous deployment process and tooling that supports multiple environments or accounts. So this is where you really don't want to have disparity. This is what can affect your customer experience the most when you deploy an application and you're like, oh, okay, our testing environment or staging environment seems pretty fine, and then you go into production and everything's different because you've kept so many differences along the way, or how you reached out pulled in variables might not have been the same. I personally encountered situations where for our staging, we had a whole different way of pulling in all our config and mapping than we did for production. And then that's another point of failure. So this is a really important factor. So we've talked or mentioned quite a bit SAM or SAMCLİ, and you might be wondering what the heck is that? It's the squirrel, which represents the AWS Serverless Application Model, SAM. This is it's an extension on the CloudFormation template style. But it's built more around serverless resources, APIs, tables, layers, and applications. And it supports anything AWS CloudFormation supports. So all the docs that are out there can be applied to a SAM template. It's built on an open specification, Apache 2.0. You can find it on aws.amazon.com/serverless/SAM. And here's an example of an AWS SAM template. So it's just 20 lines. And so let's walk through this. So at the top, we have we define that this is our version of CloudFormation template, and then we have our transform, which will be applied to it to make it work with all the features that come with SAM. And so in it, right, so at first we define our resources. First resource is our serverless function, our Lambda function. We tell it where to find its handler. We tell it what runtime we want, all the source directory for the code. And then we can apply our policies, our IAM roles. We can define, okay, in this case, it's saying, okay, it has a DynamoDB read policy. And then it can reference the DynamoDB table that we create here at the bottom of this script. So running this using the SAMCLİ immediately gives us this. Once it deploys through CloudFormation and all that, you have an Amazon API gateway endpoint, which we have defined in events there on the serverless function. And then that Amazon API gateway, it's associated with that Lambda function, which has access to our table because it has the correct role. That's all in 20 lines. And this can be turned into all sorts of complicated or large applications. This is an example here that can be found on GitHub. I urge you to go check out the AWS Labs and the AWS samples repositories on GitHub. There's a number of serverless SAM templates for all sorts of applications. So we talked about the serverless application model. Let's talk more about the AWS SAM command line interface. Now, this is a really powerful CLI tool for local development, debugging, testing, deploying, and monitoring of your serverless applications. This supports an API gateway proxy style Lambda service for API testing. This means you can test your serverless application locally with the open source Docker Lambda image that mimics the Lambda execution environment, and then have an emulated API that's local on localhost, port 3000, where you can locally test your serverless application. And then using the CLI, you can then, after you've tested locally, you can use SAM build to build all your dependencies, create your application, and then SAM package to take that application, take all the source code, create artifacts in S3, and then create a packaged YAML file, which then SAM deploy can use to create and deploy your application with CloudFormation, pulling all the necessary code. This is great, especially with SAM, since you can stub out your different environments, your different variable sources. You can create various parameters so that someone can come in, and when they deploy, they can pass those parameters in, so that on deployment it's got whatever it's needed, and that can be somewhat agnostic from your code, right? So you can have your code be a certain way, and then the resources it use can come from anywhere. And once it's deployed, with the SAMCLİ, you can tail those production logs that are occurring in CloudWatch from your function or your application. This also helps you build in native dependencies. So SAM can do quite a bit. It's not just a easy CLI built around CloudFormation. It's making things really more focused towards building serverless applications and being able to test them. Factor 11, logs. Treat logs as event streams. Logging, we believe at AWS, is a universal right, especially with Lambda functions. Any console output is automatically collected and sent to Amazon CloudWatch logs. And from there, these logs can be turned into metrics. And they can also be sent to S3 or Amazon Elasticsearch. And you do all sorts of further inspection, querying on your data. Metrics for Lambda and API gateway for several key stats are automatically collected and sent to CloudWatch. So just going into CloudWatch, once you've deployed an application, you can go straight to CloudWatch and find that you've already got a number of logs of all sorts of events and output. So say your code errors out, that will automatically be logged. And so this really helps throughout the different stages of building your application, really, again, get more visibility into what's going on. So the final factor here is run admin management tasks as one-off processes. So this doesn't apply to Lambda in the same way in that you already limit your functions based on use case. You have these single functions per action. So if we're talking administrative tasks, these would occur in their own Lambda functions. So these administrative tasks could be, migrating databases or user provisioning and whatnot. So by the nature of using Lambda, you should already be doing that. So if you have a thing where you need to migrate a database, create users, you should just create those as one function. So let's recap these 12 factors as they pertain to serverless applications. We went through talking about keeping your code base broken up in a logical way, keeping your dependencies well-versioned, having different configs for different staging environments, making sure you have a nice clean build, release, run pipeline, and things like having visibility into your applications, make sure that you're building them efficiently. We talked about dev and prod parity and how that's important, and all the different ways you can get logs, and just these general ideas of how to go about building a smart application, right? So in closing, we want to always make sure that throughout building any form of application, especially within a serverless application, that you're thinking about code reusability, whether that's with how you organize your code such that any new incoming developer is able to find what they need to find and know inherently what resources are important to what part of your code base. They know, where to get the different configs for different staging environments. They know, where to find their dependencies, whether those, if you have those in a Lambda layer, that's naturally, you can version that and keep that consistent across your org and code base. And doing this will truly save you hours and hours of developer time and operations time. We looked at factors related to underlying process management, network ports, concurrency, and admin processes are not largely an issue in serverless due to just the nature of how Lambda's product is designed and all the various features. We looked at best practices for serverless aligned pretty closely with these 12 factors. So just by creating a serverless application on AWS services, you might have likely already reached the bar for 12 factor. The rest becomes more about the philosophy of how you go about building your application and organizing all your code. To find out more about the serverless application model, you can visit aws.amazon.com/serverless/SAM. Again, this is a very powerful model. We saw in 20 lines, we were able to create a REST endpoint with the serverless compute that had access to a database. That is the core of what you would need to build, a CRUD database or the back end of an application. And of course, these can get much more complex, and since it supports CloudFormation templates, all of the same features that you've come to know and love are accessible. You can also visit aws.amazon.com/serverless to find out more about all the different ways you can build serverless applications. Thank you for listening. My name is Mohib Zara. I hope you have a wonderful time at reInvent.